Hello everyone, welcome back to the channel. Today I'm going to be explaining how to design a common emitter transistor amplifier with a specific gain, specific cue point, and kind of go through some of the basic math to create a reliable amplifier that can be used for audio frequencies and potentially into some low frequency RF in the megahertz range. So I have a couple equations written down here and then a bunch of circuitry stuff going on here, and I'm going to go kind of dive into these first, and then we'll go into the step-by-step process that I made. It's about 8 steps on how to accurately design one of these for the specific gain. And then later on in the video I'll go into LT Spice and simulate the circuit that an example circuit that we're going to work out on here, and we'll see how the gain checks out. So now we're going to look at this circuit here and these equations here. You can see in this circuit I have 4 resistors, RB1, RB2, RC, and RE. And these are going to set up the cue point or the DC operating point as well as your gain of this transistor amplifier. And then we have the transistor right here. And these 2 capacitors are what's known as AC coupling capacitors. What this is allowing you to do is input an AC waveform here whose center is at 0 volts, amplify it, and have it ride on top of a DC signal in here. And once you amplify it, comes out here on a DC signal, but only AC can pass through this capacitor. So on the output, you'll have a much larger signal still centered around 0 volts. On this side, I have a couple equations here. This equation you don't have to pay too much attention to, but the rest of these you should pay a little more attention to. So you can see here, I have this little equation here. Little r sub e equals Vt over Ic. Vt is what's known as the thermal voltage, and it's typically at room temperature around 0.026 volts. That's a key number that you have to keep in mind when building these transistor amplifiers. I'm not going to go into what that is coming from in this video, but I may go into it in later videos. Now Vt is being divided by I sub c. I sub c is just the amount of current that's actually flowing into the collector of the transistor. So by knowing these 2 values, what ends up happening is you have a diode here, and you can approximate that diode across the base emitter junction as a resistor whose resistance is determined by this equation here. Once you know this, then you can move on to this third equation, A, where A is the voltage gain of this amplifier. And you can see that the voltage gain is determined by RC over the sum of RE, big RE, plus little re, which we found in the previous equation. That is what completely determines your gain. Now the bias point and everything will also determine your gain, but when you do the biasing correctly on this voltage divider here, your gain is going to be very close to what you come up with. Next equation, IBB, is around 10 times IB. What is this saying? So bipolar junction transistors are known as current controlled transistors. So what happens is you put in a small amount of current into the base and you get a larger current flowing through the collector. Now with that you do have current running through the base, which when you're setting up your voltage divider here will start to steal current from the divider. So to keep the voltage at this point on the base relatively stable, you want the current that's flowing through RB1 and RB2 to be larger, or much larger, than the current that will be running into the base during operation. This will keep the base voltage very stable and will allow you to have a very stable output. Next, IC equals beta IB. This is the equation for the transistor. This is showing you how much current gain you're getting through this transistor. Beta for today's transistors is around 500. So what that is saying is that if I put 1 milliamp into the base, I will get 500 milliamps flowing through the collector. Now that sounds great. However, one thing you have to note is that beta, even across transistors made on the same day, on the same chip, with all the same components and machinery, the beta will vary. It will always vary. So it's actually bad practice to design an amplifier solely based on the beta of the transistor. Now, because we're setting our gain relative to the collector resistor and the emitter resistor, we actually don't rely as much, or at all really, at the beta of the transistor. And when we go into LT Spice, I will show you guys the same amplifier setup with a completely different transistor with a beta that is much less or much more. And you'll see that as long as your current gain is sufficient in that transistor for the gain that you want, the gain output of the whole circuit will always be around what you want. Lastly, this last equation here, I sub E equals IB times beta plus 1. Where did I get that? Well, if you look here, you have IC running into the collector of the transistor, and you have IB running into the base of the transistor. So those currents have to go somewhere. And where do they go? IE. From this equation here, IC equals beta times IB, that is essentially what is written here. So you have IB times beta, which is your collector current, and then IB times 1, which is just your base current. So this is what's determining your emitter current. However, like I said earlier, beta is typically pretty large now, around 500. So we can actually make, later on, that I'll show you in the video, we actually make an approximation of IE being roughly equal to IC because beta is so large that this plus 1 really does not add much to the whole circuitry. And this will just simplify things a lot for us when we start actually designing the amp. All right, so I've done a lot of pointing, a lot of explaining. So now I'm going to show you the step-by-step process that I've come up with for designing common emitter transistor amplifiers with a gain that's around 10% the value that you want. And here they are. So, step 1, determine IC at DC, typically around 1 milliamp. You choose what you want your IC or your DC operating current to be of the transistor amplifier. I typically do around 1 milliamp. You can go a little higher. You can also go a little lower. It's really up to you, just depending on the resistor values that you have. Next, set RC, this resistor here, such that VC, which is the voltage at the collector, is around your supply voltage divided by 2 at DC. So, if I have a supply voltage of 5 volts, I want VC to be around 2.5 volts. And what this is going to allow me to do is get the maximum swing of my output voltage. Because if I was to bias it somewhere lower, what would happen is when I input my signal, I'd start getting really awful clipping. And the output signal will not look at all like the input signal. So by raising that bias up, it actually lets me get the full swing of the output voltage that I want. Next, you determine little r sub e, which is the resistor approximation we used for the base emitter diode junction, using Vt over IC, and IC is your DC operating current through the collector. Then you use equation 3, the gain equation, to determine Re with the gain that you want, little r sub e, and the collector resistor that you set right here. Now, assume that I sub e, the current flowing through the emitter, is roughly equal to the current flowing through the collector. You can use this to determine the voltage at the emitter of the transistor using the R sub E, the big R sub E value that you found in step 3. From there, you set VB to VE, your emitter voltage, plus VBE. Now, like I said earlier, there's a diode junction here. And a typical silicon diode, which a lot of transistors are made of today, they have a 0.65 volt drop across them. So all you have to do to find the voltage at the base is add 0.65 to the emitter voltage here. Now, we use I sub B equal to I sub C divided by beta, and you set IBB to be 20 times IB. So what I'm doing here is I'm using a typical beta value of around 100, and you can use 100 for most amplifiers. And the collector current that I found that I determined in step 1 to find the base current that will be running through the transistor. Once I have that base current, I set the base bias voltage divider current equal to be around 20 times the current that's actually running through the base. And this will give me a stable voltage divider biasing right here at this point at the base. Finally, you know VCC, you know the voltage on VB, and you know the current running through RB1 and RB2. So using some basic Ohm's law, you can find the values of RB1 using this equation and RB2 using this equation. And from there, you have designed an amplifier. All you need to do is add some decoupling or AC coupling caps, and you're good to go. So I've done a lot of pointing and explaining, but now we're actually going to work through an example. So here I have the circuit from the last page, and I have some conditions that I've set myself. So first, I want the collector current at DC to be around 1 milliamp. I want to run this amplifier off of 5 volts, and I want the voltage gain to be roughly 10. So we've already completed step 1, which is set IC, so step 1 is complete. Step 2 is to set RC such that VC is roughly your supply voltage over 2. So I want VC equal to 2.5 volts. So to do that, I take Ohm's law, V equals IR. I set it equal to the difference in my voltages across this resistor, which in this case is just half of the supply voltage. So 2.5 volts. And I have 1 milliamp running through that resistor, and that is going to be times RC. So rearranging this, RC equals 2.5 over 0.001, which equals 2.5 kiloohms. And that is what RC is. Next, we need to find little r sub e with the equation Vt over Ic equals little r sub e. Now if you remember, Vt is the thermal voltage, and that is at room temperature. We're going to assume this amp is running at room temperature, is equal to 26 millivolts. Now Ic is 1 milliamp. So what we have is r sub e, little r sub e, equals 0.026 volts divided by 0.001 amps. And so 0.026 divided by 0.001 is 26 ohms. Now, that is 26 ohms. Now, using the gain equation, which is A equals RC over big RE, this resistor here, plus little r sub e, we can rearrange this to find big R sub e. To do that, I'm going to move this over. So big RE plus little r sub e equals RC over A. So big RE equals RC divided by A, which is our gain, minus little r sub e. Plugging in all the values that I have up here, I have RC, which is 2.5 K, divided by 10, minus 26 ohms. Using this, big RE equals 224 ohms. Now that we have the value of R sub E, big R sub E here, step 4 is to actually determine the voltage on top of the emitter resistor. We can use that using Ohm's law and the fact that I sub E is roughly equal to I sub C because the base current contribution is very small. So again, this is just a basic Ohm's law problem. V equals IR. We know the current and we know the resistance, so we can solve the voltage, which equals 1 milliamp, 0.001 amps times 224 ohms, which equals 0.001 times 224, 0.224 volts. Using this and the fact that we have a diode drop across the base emitter junction, we add back that diode drop of around 0.6 volts to actually find the voltage here at the base of the transistor. So if we add 0.65 volts, we find that VB equals 0.874 volts at this point. Now, we need a little more information before we can actually start building this resistor divider. We need to find the actual base current flowing through here. And for most transistors, you can assume that beta is around 100, like I said earlier. And we know that I sub C, the collector current, equals I sub B times beta. So rearranging this, we can find that IB, or the base current, equals 1 milliamp, 0.001, divided by 100, which equals 10 microamps of current flowing into the base. So, in order to set up this voltage divider right and to have a stable bias voltage, we want IBB, or the base bias current, to be equal to around 20 times this. So this is going to be equal to 200 microamps of current flowing through these two resistors. So, step number 6 and 7, we know the voltage here, and we know the current flowing through both of these resistors, so we can solve for these resistors. So, RB1, the equation for RB1 is going to be VCC minus VB over IBB equals RB1, which equals 5 minus 0.874 volts divided by 200 microamps. So plugging that into the calculator, 5 minus 0.874 divided by 200 microamps gives us a value of 20.63 K. Equals RB1. Now, step 7, find RB2. We know the voltage across this is just VB, so 0.874 volts divided by 200 microamps is 4.37 kiloohms equals RB2. Now we have everything we need except for these AC coupling capacitors. For audio frequencies, you can generally stick to around 0.1 microfarads or a microfarad for lower frequencies. Anything above that is a little overkill, and as long as you can get your AC signal in at audio frequencies, you're good to go. Now, the process here is going to change drastically when we start getting to RF amplifiers, but I'm not going to go into that in this video. So instead, what I'm going to do, like I said earlier, is I'm going to whip this circuit up in LT Spice, and we'll see how the circuit functions. All right, so as you can see here, I'm in LT Spice, and I've built up the circuit that we just designed. So this voltage source here is set to 5 volts, like we determined, and this is my input. You can see it's a 1 kilohertz sine wave, and its amplitude is 10 millivolts. However, what I've noticed here is that the output is actually 20 millivolts, and there's a reason why, which I'm not going to get into in this video, but it has to do with the impedance, the input impedance of the amplifier. For audio frequencies like 1 kilohertz, it's not going to matter, but once we start getting into RF amplifier design, we're going to have to actually do the hard part and match the transistor. So, with all that set aside, I've gone ahead and run the simulation, and if I probe the input here, you can see 10 millivolt peak-to-peak signal, right? Now if I probe the output here, and remember these are AC coupled, the output is this blue trace. And you see we have gain, we have voltage gain, but we wanted a gain of 10. So if I get out the probes here, and I probe the very peak of this waveform, the very trough of this waveform, on this window here, 196 millivolts out of this at this point here. Now if I change the cursors to the green trace to see what the input is, 19.96 out in. So 196 millivolts out divided by 19.9 is a gain of 9.8, which is well within 10% of the gain that we wanted for this amplifier. Now, this amplifier does not have any sort of output impedance matching, and what can happen is when you start putting a load here, this output voltage is going to drop. So in future videos, I'll go through how you have to take the load voltage or the load resistance, load impedance into account. And that's going to be a huge thing when we start going into RF amplifiers, as most of RF and a lot of RF is just trying to get everything to be 50 ohms. In this case, I didn't do that. This is just for audio frequencies, but that's the eventual goal. So now you guys should have a good way of being able to just whip up a very quick NPN transistor common emitter amplifier, voltage amplifier. In later videos, I'm going to hopefully go through how you can actually make the output impedance of this much lower, and that's going to be using a common collector to also amplify the current. So we'll get into that in a different video, but I hope you guys enjoyed this. Please let me know what you guys thought of the new Lavalier mic that I got for recording in the real world, and let me know if the camera angle that I had for the writing and everything was all right, because that is the easiest and most comfortable way for me to do it. But if you guys don't like it, I can figure out how to switch it. So yeah, thanks for watching.